Hello guys, welcome back to Math Zone African Motives. Still working on mathematics N3. In this platform, we shall just have an introduction part, which is important in our trigonometry. That is the application of our trigonometry, which is very, very important in the simplification part. We have the simplification that we are going to have the solving of equations, but before that, we just need to know the relationship that we have in our trigonometry. So I'm going to start by explaining the basic part, which is the right angled triangle concept. So we have got our right angled triangle in this case. On a right angled triangle, there are some properties that we just need to understand, which are very, very important in the simplification of our trig identities and also the solving of equations later on. Given a right angled triangle, which means that we've got a 90 degrees on this triangle, depending with the angle that you're going to have in this triangle, if you are given the angle that is referred to as theta in this case, this angle determines the sides that we are given on this triangle, the one that is opposite, the one that is adjacent to the 90 degrees, and the hypotenuse, which is always the longest side. All right, so that means the angles, they are created according to this angle. The sides are created according to the angle theta. That is here, we are going to have the opposite. Here, we are going to have the adjacent. The one that the 90 degrees and the theta are on the same side is your adjacent. Then the hypotenuse, the one that is opposite to the 90 degrees, that's the longest side that you can ever have. So what I'm trying to say is that the triangle that you are given, if you are given a triangle like this, and this is your theta here, this is where you have your theta. According to this triangle that we have, it means this becomes our opposite side. This side is now opposite to theta. So here we are now having opposite, and this where theta and 90 degrees are on the same side is now your adjacent. So it means we now have the adjacent here, and always opposite to the 90 degrees is our hypotenuse in this case. So what I'm trying to say is that the theta is the one that determines our sides, the one that you're given, especially the adjacent and the hypotenuse, the adjacent and the opposite, because the hypotenuse is always opposite to the 90 degrees. So this one, whether you are having theta on which side, the hypotenuse does not change. All right. So from this, we have got the basic 6 trigonometrical ratios that we need to understand. So we have got the basic 6 trigonometrical, let me just rate as trig ratios, in this case, trigonometrical ratios, which we need to apply in our syllabus from this same right angled triangle, which are the best, the first 3, or all of them actually, are being taken from our SOHCAHTOA concept. So we have got the SOHCAHTOA concept, which gives us the ratios. All right, so this is SOHCAHTOA, whereby we are dealing with the sine of theta, the cosine of theta, the tan of theta. So we are saying the sine of theta is opposite over the hypotenuse, adjacent over opposite over adjacent. So that is how we can take our ratios in this case. So we've got the sine of theta being equal to the opposite over the hypotenuse in this case. So you can just write as opposite over the hypotenuse, just with h, if you want to just shorten opposite over hypotenuse in this case. All right, then we have got the cosine of theta, which is cos theta is in this case adjacent over the hypotenuse. So that one is going to be adjacent over the hypotenuse. Then we've got the tan of theta, opposite over the adjacent, which is just opposite, which is O over the A. All right, so that the tan of theta is going to be the opposite over the adjacent in this case. So these ratios can be taken from our right angled triangle now, depending with where your theta is according to the diagram. All right, then from these 3 ratios that we have here, if we are to divide each ratio by 1. All right, if we are to divide each and every ratio that we have here by 1, let us see what is going to happen. We divide sine of theta by 1, that's 1 over the sine of theta. We are going to obtain cosec theta. All right, the same thing for cos. If we are to divide 1 over the cosine of theta, we are going to have the sec this time. So 1 over the cosine of theta is equal to sec theta. So what it simply means is that if I am given 1 over cosec, if I am given 1 over cosec of theta, it is going to give me the sine of theta, which is the opposite. The same thing, if I'm given 1 over the sec of theta, it is going to give me the cos of theta in the other way. That is what I'm trying to say in this case. All right, then we put 1 over the tan of theta. This one is going to give us the cot of theta. So 1 over tan, it's cot theta. And also you need to understand that this tan of theta can be written as, I want us to check what is happening or where exactly we got this one, that the tan of theta can be written as the sine of theta over the cosine of theta. So we are saying it's sine over cos. So if we said tan, 1 over tan, it's cot. So it means we can write the same way as cot of theta is equal to, which is now, we interchange these two. So it is going to be the cos over the sine of theta in this case. All right, so this is what we can take from the tan of theta. Okay, so like I said, I want us to formulate and see where this was actually taken from. Let's just not say it's something that just came. If we say sine over cos, remember tan is opposite over adjacent. This is tan. All right, let's see what's going to happen. If we say that tan of theta is equal to sine theta in this case, sine theta is equal to opposite over the hypotenuse. So we have got opposite over the hypotenuse in this case, divided to the cosine of theta, and the cosine of theta is adjacent over hypotenuse. So we are going to divide to the adjacent over the hypotenuse in this case. So these two are dividing each other, which we know that we can write as opposite over hypotenuse times. The moment you are dividing in this case, you are going to introduce the multiplication and you interchange the second fraction. So this is going to give us hypotenuse over adjacent. So as we can see, this one and this one cancels. You remain with opposite times 1, which is opposite over 1 times adjacent, which is adjacent. And what is representing opposite over adjacent? It's tan. Opposite over adjacent, this is tan. So that's why we are saying that tan of theta is truly sine over cos, which is, this is sine and this is cos. All right, so this is where this part was actually taken from. All right, so with this part, let us introduce another, let us have another part again, which is important that we are going to need, which is some of the identities that are needed in our syllabus. We have got the Pythagorean identity, that is the first part, the Pythagorean or the square identities in this case. All right, so we have got square identities. That's identities in this case. Where are these identities being taken? Where are we taking these identities from? If we are to check here, we said we can refer on this part from our normal triangle. We've got opposite, adjacent, and we have got what? The hypotenuse in this case, which we know that on a right-angled triangle, this can be referred, we can take or use our Pythagoras theorem, because we know that on a right-angled triangle, this is what we have in this case. We said according to the angle theta, we are going to have the sides, which is this one adjacent, this one opposite, and this one being our hypotenuse. In terms of the Pythagoras theorem, we are saying the hypotenuse squared is going to be equal to opposite squared plus the adjacent squared. Whereby here, if we are to, okay, let us say we divide each and every term here by h squared. I want you to see where these ones were taken from. If we are to divide by h squared in each and every term in this case, so here we are to divide by h squared each term. All right. So if we are to divide each and every term by h squared, that means here we are going to have something like h squared over h squared is equal to opposite squared over h squared, which is equal to, that is a plus adjacent squared over h squared in this case. All right, so this one definitely cancels. We remain with a 1 in this case, which is equal to, there's a squared, so we can write this as opposite over hypotenuse squared. So this can be written as opposite over the hypotenuse squared plus, here also there is a squared and a squared, so we can write this as adjacent over hypotenuse squared. So this can be written as the adjacent over the hypotenuse squared. But let us see now what is happening. Opposite over hypotenuse, we know this ratio is not just a common ratio that we see. Opposite over hypotenuse represents sine of theta. Opposite over, that is the sine of theta. So meaning to say, where there is opposite over hypotenuse, here we are going to replace with the sine of theta. So this is going to be sine theta, but being squared, plus adjacent over hypotenuse. Again, this we have it from the cosine of theta adjacent over hypotenuse. So that means we are going to replace this with a cosine of theta, but being squared. All right, so this simply means sine squared like this simply means we are writing as sine squared theta plus cos squared theta simply means cos squared theta like this. So this is the Pythagorean identity that we are talking about, the first identity that we are supposed to note in our syllabus. That's where it was actually taken from. You'll be given this in your formula sheet, but you are supposed just to at least understand, like, since this is introduction, to understand where it was actually taken from. All right, so I'm going to list these identities. So we have seen that we are going to have 1 which is equal to sine squared plus, but I'm just going to write this as sine squared of theta plus cos squared of theta is equal to 1. All right, so this is our first identity. The second one, if we are to take this first identity that we have now, if we are to take this identity that we now have as, let us just have it aside here, that is 1 is equal to sine squared theta plus cos squared theta like this. Let's say you divide by cos squared, divide each and every term, this time by cos squared theta, just like the previous part, but this time we divide, let's say, by cos squared theta. I want you to see what's going to happen. If we divide by cos squared theta, it means we are going to have 1 over cos squared theta is equal to sine squared theta over cos squared theta plus cos squared theta over cos squared theta. We are dividing each and every term. But from our ratios, we said 1 over cos, it's a sec. If we still remember here, 1 over cos, it's a sec. So this is going to give us sec theta. But now there's a squared here. If we are to check, this is 1 over cos squared. So it is going to be sec squared theta, which is equal to sine over cos. Remember that sine over cos is tan, but there's a squared and a squared. So it's going to be tan squared theta. And here we've got cos and cos cancels. So this is going to give us a 1. So it's another identity, meaning to say 1 plus tan squared is equal to sec squared. So we are going to have another identity. Also, you are given this, but here I just want you to see where it was formulated from. So 1 plus tan squared theta is equal to sec squared theta. So using this, you can also prove for the other one. If you divide now by sine squared, I want you to prove divide by sine squared each and every term. We are going to see that at the end, we are going to have 1 plus cot squared theta, which is equivalent to cosec squared theta. So these are the Pythagorean identities, or the square identities, which we are going to need in our syllabus. We are going to need this part. So you'll be given actually in your formula sheet. So what you need is to know how to use them later on. But here I want you to see where they were taken from. and how you're going to apply it. All right, then the other part that we are going to be focusing on again is to know the relationship. This one is very, very important, the relationship. All right, so we need to know the relationship between angles. So we have got the relationship between angles, but this relationship is between the positive and negative. So I'm just going to write in short, positive and negative angles in this case. All right, I want you to see what is the relationship that happens between angles. Angles can be taken as positive or as negative, which some of us do not consider much. So I'm not going to explain this much because in our syllabus, we just take mostly we work with the positive angles, but you need to know the relationship between a positive and a negative angle from quadrants. All right, if you are given a quadrant like this, all angles that you take in the anti-clockwise direction are referred to as positive, and all angles that you take in the clockwise direction are referred to as negative angles. So it follows that the angle that is at a point, if you represent an angle at a point, like let's say an angle in the first quadrant like this is the angle that you are representing as maybe 30 degrees, or maybe it's 50, whatever angle that you have. It's a positive angle, this one. This angle is going to be equal to the angle taken from the same point to the same region or to the same condition where there's this 30 degrees here. These two angles, they'll be equal, but this one, because of the direction, it's a negative angle. And how are you going to find this angle? Angles at a point that up to 360. So if we subtract 360 minus 30 degrees, we obtain 330 degrees. But this angle is going to be taken as a negative. So it means this angle here, the whole of this angle is minus 330 degrees. So what is the relationship between these two angles? These two angles, they have the same properties. The angle of 30 degrees is equivalent to the angle of minus 330 degrees in every property that you are going to talk about. Let us just say sine of 30. We are simply saying the sine of 30 degrees will be equal to the sine of minus 330 degrees. If you use your calculator, you're going to obtain same answers there. These two, they are very, very equal. All right, so I'm not gonna talk much about this. I want us to quickly rush to our quadrants and explain more about our quadrants, having exact angles in our quadrants. All right, so we're going to talk about having the exact values or exact angles in quadrants in this case. All right, the use of quadrants is very, very important. We need to know our quadrants concept. All right, so I'm going to explain this way. Given a quadrant, given the concept of a quadrant, we are simply referring to the to dividing this quad 4 equal parts. We are going to divide into 4 equal parts, meaning to say these angles at a complete revolution, they are equal to 360. So divide by 4, we are going to have 90 degrees. So these angles, they are divided 90, 90, 90, 90 from each point, whereby this angle at the reference point in the horizontal axis to the right, it's at 0 degrees. But remember what I was saying, angles taken in the anti-clockwise direction are referred to as positive angles. So meaning to say our angles are going to be taken as positive angles, plus 90 degrees, 180 degrees. We add 90, it's 90, 90. So if we add 90 here, 180 plus 90, you are going to obtain 270. 270 plus this 90, you are going to obtain 360 degrees. So meaning to say at the reference point, the angles that lie at the reference point, it's 0 degrees and 360 degrees. So what is the concept of these quadrants? It follows that from the cast concept, concept, or you can use all students take calculus, or you can use whatever concept all stupid teachers copy. I don't know which part is best for you, or you can just use the cast concept to fill in to say, this part represents to say that every quadrant can be referred to as a positive or negative in terms of the trig that is operating in that quadrant. But these trig that we are given here, they are positive in their corresponding quadrants, starting with the A from 0 to 90 degrees, which is our first quadrant. So this is our first quadrant, this is our second quadrant, this is our third quadrant, this is our fourth quadrant. So having the first quadrant from 0 to 90 degrees, these angles which lie from 0 to 90 degrees, we are saying in terms of their trigonometrical ratios, all of them, they are positive. So the A is for all. So all trigonometrical ratios in between 0 to 90, they are all positive. The A, remember the letter in the quadrant represents, that is the one that is positive. If we move from 90 to 180, sine, S is for sine. So it means sine is one that is positive in this case. So what is going to happen with sine? What is going to happen with cos in this quadrant? It means cos is going to carry a negative. Tan is going to carry a negative because this is the quadrant for sine. If you move from 180 to 270, you are now talking about tan. Tan is the one that is positive in this case, meaning to say sine is going to be negative, cos is going to be negative because it's for tan. From 270 to 360 in the fourth quadrant is the cos, which is positive. So meaning to say the rest of the identities, talk of sine, talk of tan, they're going to be negative in this quadrant. So how do I then relate from a normal angle or from a certain angle to the normal quadrant that I'm using? All right, what I'm trying to say is that we want to reduce angles which are not acute angles, which are greater than, depending with the quadrant that you're going to have. It follows that in each quadrant, you're going to have something like this. In each and every quadrant, there is an acute angle which lies in each quadrant taken from the horizontal line. Let's say this is x. In the second quadrant here, there's going to be x here. In this quadrant, or there's going to be x at this point. In this quadrant, there's going to be x at this point. The angles, they're always taken from the positive to the line. I mean, from the horizontal line to the angle, to the line that you're given. Horizontal line to the line that you're given. Horizontal line to the line that you're given. So it follows that in the first quadrant, in this case, the angle that you're going to be taking with is the x as it is. You're going to refer this angle as x, direct x as it is. But in the second quadrant now, we are going to see that the angle that you're going to take is taken from the positive horizontal going this direction, which is our positive angle. So we are referring in terms of positive angle. So this whole angle, what is going to be this angle? Take note here, we've got a straight line. And the only angle that is affecting on this straight line is this x. This is the angle that is not part of the angle that is indicated here. So what are we going to do? We are simply going to subtract this x from 180 degrees. So in the second quadrant, our angle is going to be 180 minus x. We are going to be talking of 180 degrees minus x. In the third quadrant now, we are going to see that this is the angle that we are going to take from this point up to this point like this. So meaning to say we are going to talk about the 180 being involved as part of our line. And this angle is also taken into consideration. It's part of the angle. So we are going to add this time. So this one is going to be okay, let's write first the third quadrant, all right? So this is the third quadrant. So this angle is going to be given as 180 degrees plus x. X is involved in the 180 degrees. You have to add, all right? Then in the fourth quadrant, what is going to happen in the fourth quadrant? This is the angle that you're going to take always from the positive going in this direction in the anti-clockwise. This is the angle that we want to indicate this one. So we are only left to reach the 360 degrees, but we are not because of this x that is stopping us to get to 360. So what are we going to do? We are simply going to subtract from 360. So this angle is going to be 360 degrees minus x. All right. Knowing how the angles are taken in each and every quadrant now is going to help us to reduce these angles, because we said this quadrant from the cast concept, we remember we talked about the cast concept like this. This is our cast concept, or all students take calculus. It is going to follow that in the first quadrant. All right, let's talk about the first quadrant. It is going to follow that all angles are going to remain as they are. If you are given x, we are going to just remain with sine x. If you are given x for cos, we are going to, and these all angles, they are going to be positive. All of these ones, they are positive. Remember, A is for all. So all these ratios, they are positive. So it follows whatever that affects this ratio or these ratios. Remember, we talked about 1 over sine x being equivalent to what? To cosec x. 1 over cos being equivalent. So those ratios also, they are going to be positive because of what? Because their corresponding ratios, these ones, they are positive. So it also means that the cosec of x also is going to be positive. The sec of x is going to be positive. The cot of x also is going to be positive in the first quadrant. That is what we need to understand there. But now, okay, maybe the second quadrant is one that can explain this one much better, because here it does not give us the good explanation. Okay, well, let us take the explanation from this way. In the second quadrant, we are saying in the second quadrant, the angle that is operating there is 180 degrees minus x. This is the angle that operates in the second quadrant. So meaning to say, yes, this is the angle that is operating, but in this quadrant, it's for S, for sine. It's sine only, which is positive, sine only. So that means we are going to have the sine of 180 degrees minus x reduced to the sine x, reduced to the sine x. Now we are reducing this to sine x, but it is going to carry a positive. We have reduced this to sine x, but carrying a positive. So this is going to be equivalent to positive sine x. Why positive sine x? Because this is the quadrant for sine. Sine is positive in this quadrant. But what is going to happen with cos? The cosine of 180 minus x, we are going to reduce it to the cos of x, which is fine. But now in this quadrant, cos is not positive because it's a quadrant only meant for sine, meaning to say cos there is negative. So it is going to be negative cos of x. The same thing is going to happen to the tan 180 degrees, tan 180 degrees minus x. This is not the quadrant for tan. It's for sine, but we are reducing 180 to x. So it is going to be equal to minus tan x. That is the concept. So you need to understand this concept, each quadrant, how it operates. All right, let's go to the fourth quadrant. In the fourth quadrant, we are going to see the same concept or the same application. This time, all right, let me just write our angle so that we do not confuse. So in the first quadrant, our angle is x. In the second quadrant, our angle is given as 180 degrees minus x, remember here. In the fourth quadrant, our angle, why am I rushing to the fourth? We are now in the third quadrant. All right, so here we are in the third quadrant where our angle is 180 degrees plus x, 180 plus x. And this quadrant is, the second one is for sine, the third one is for tan. So meaning to say tan is going to be a positive, the rest will be a negative. So let's start with the side in this case. So the sine of 180 degrees plus x is going to carry a negative because this quadrant is not for sine, it's for tan. Cos also, the cosine of 180 degrees plus x is going to carry a negative. So that will be negative cos of x. Then the tan of 180 degrees plus x. This one is the one that is going to carry a positive because in this quadrant, tan, it's a positive. So that will be positive tan x. All right. So this is our third quadrant. Then we've got our fourth quadrant. So let's see the application of the fourth quadrant. In the fourth quadrant, our angle, remember our angle in the fourth quadrant is 360 degrees minus x. But cos is the one that is positive here. We are referring to cos. Everything is going to be negative. So that means the sine of 360 degrees minus x is going to be equal to minus sine x. Then the cosine of 360 degrees minus x. This one is going to be positive because it's the quadrant for cos. So it is going to be positive cos x the tan of 360 degrees minus x is going to be equivalent to the minus tan of x, because we said only cos is positive, the rest will be negative. So that's how we are going to use these quadrants. So this one is very, very important. You are not given some of this information in your formula sheet. So you need to know now the concept that is happening between these angles, the relationship between your quadrants, and how to manipulate whatever formula that you are given. So like I was saying, it follows that if you understand that, if you understand this concept here, what does it simply mean? It simply means here, let us explain from the third quadrant, what I was trying to explain here in the first quadrant, to say if sine is positive, therefore cosec is positive, sec is positive from cos, and tan. Why? Okay, I'm seeing here there's supposed to be a tan there. I hope we saw this one before. So if we are to use this concept, we are going to see that sine here, it's a negative on the other hand. And we know that 1 over sine is cosec. So it means the cosec of 180 degrees plus x is going to be a negative in its simplification. The cosec reduced to sec to x itself, it is going to be a negative of cosec x, just like what we are seeing in the sine, because the sine is negative. So the same with what affects the cos, it is going to be a negative. What affects the tan is going to be a positive, meaning to say cot here of 180 degrees plus x is going to be positive, the cot of x, because cot is positive there. I mean, tan is positive. So whatever that carries tan must be a positive. Whatever that carries sine must be a negative in its equivalent also. All right, so this is the application of our quadrants. Then the last part that we are going to have is the special angles, which is also important in our syllabus. We are going to see the use of this in our next class. We are going to be applying now question papers and revisions so that we see how to use this part of our introduction. All right, so we've got the use of the special angles. You need to understand the special angles. The special angles, these are angles that we can have their equivalent trig in, we can have their equivalent or exact values without using a calculator, which are the angles of 30 degrees. We talk of 45 degrees. We talk of 60 degrees and 90 degrees. These are the special angles that we are going to be talking about. These angles being referred in radian and degrees. I mean, these angles being in degrees. So you can even convert these angles to radians, because we know that the relationship states that pi radians is equal to 180 degrees. So meaning to say, if you want to find 30, you are going to ask yourself, 30 degrees is equal to how many radians? So that's 30 over 180 times pi. So if you multiply 30 over 180 times pi, in this case, what are we going to have? We are going to obtain something like pi over 6. So meaning to say the same angle of 30 can be given or can be written as pi over 6. All right, so let me change this one to this. So this can be given as pi over 6 in radians, same as 45. Here we are going to have 45 over 180. So you're going to obtain pi over 4. 60 degrees, 60 over 180, which is going to be pi over 3. 90, which is going to be pi over 2. So these are the equivalents of these angles. If you are given these angles, you must be careful, because they are still representing to the same special angles, but this time they are giving these in radians, but still they are our special angles. So what is it that is special about these angles? We can determine their equivalent from triangles direct as if we are using a calculator, whilst we are not even using a calculator. Let us start with the angle of 45 degrees. Given a right-angled triangle, that is a right-angled triangle at 45 degrees, 90 minus 45 is going to be 45, or if we add angles in a triangle, they must be 45. So this one is an isosceles triangle whereby these two sides will be equal. So let's say this side is equal to 1 and also this side is equal to 1. It follows that from our Pythagoras theorem, h squared is equal to 1 squared plus 1 squared, whereby h squared is going to be 1 squared plus 1 squared, which is 2. So to find h, you're going to introduce the square root where h is square root of 2. So this side is going to give us the square root of 2. So we can determine the ratios. In this case, we talk of cos of 45 degrees. Remember cos before from our SOHCAHTOA concept. We talked about the SOHCAHTOA concept where we said cos is adjacent over hypotenuse. So depending, I don't know which 45 we're going to take, but let's work with this one. So it's going to be, if we work with this one, our adjacent is going to be 1 in this case, adjacent over hypotenuse. That is 1 over the square root of 2. Which from your surds, remember we can rationalize this from our surds, multiply by square root of 2, square root of 2. What are we going to obtain at the end? 1 times square root of 2, that will be square root of 2 over square root of 2 times square root of 2, which is 2. Remember from your surds, the square root of a times square root of a is equal to a. So you've got 2 and 2, which is going to be a 2. So that's, this value is the one that you get exactly on your calculator. So it means that we can obtain or we can use the special angles. But now there's nothing special about these angles because now our calculators, they are very, very reliable. They can give us the exact value that we are looking for, which is direct. So what I'm trying to say is that, yes, you might need this information just for the revision sake, but there's nothing now that we can consider special about these ratios. I want you to see on your calculator in degrees, cos 45 degrees like this, we get square root of 2 over 2, of which on your syllabus, or to use this to say it's cos 45 and I wrote square root of 2 over 2 like this. This mark does not even keep, so where is it actually coming from? There is a part that we can just at least understand how to have this one. So if you check, but there's nothing very, very important because our calculators, they can give us exact values as fractions, whatever that we want or whatever that we are looking for. These are the exact values that we are referring to, and these are the ones that we are obtaining from our from our triangle here. All right, so it is the same thing. The sine of 45 is going to be opposite over hypotenuse, so it's going to be 1 over the square root of 2. So as you can see, 1 over square root of 2, we worked it before here. 1 over square root of 2, we ended up with the square root of 2 over 2. Then we move on to the tan of 45 degrees in this case. So the tan of 45 degrees, opposite over adjacent. So opposite over adjacent, that's 1 over 1. So meaning to say tan 45 is equal to 1. All right, so I think on this one we are done. We are going to move on to another triangle that is going to give us the other angles, which carries, which is taken from 60, 60. If this angle is 60 here, if this angle is 60 and this angle is 60, it means it's an equilateral triangle. So if we divide it into 2 equal parts, this angle here is going to be 30 degrees and this angle is going to be 30 degrees. This at what? At 90 degrees. All right, so now this is not important. We can just use one of the triangles, but you can use both, but we can just use one. As you can see, those two triangles are the same. So let's say this is 2, this is 1, this is going to give us the square root of 3. So that's where we can obtain our ratios, the cos of 60 degrees, the sine of 60 degrees, the tan of 60 degrees, 30 degrees also, the cos of 30 degrees, the sine of 30 degrees, the tan of 30 degrees, and so on. All right, so that's it. So the cosine of 60 degrees, which is according to 60, remember cos adjacent over hypotenuse, so it's adjacent over hypotenuse, which is 1 over 2. Then the sine of 60, opposite over hypotenuse, so the opposite there, which is a square root of 3 over 2. The tan of 60, tan opposite over adjacent, which is opposite over the opposite, sorry, here, opposite of 60, we are talking about 60. So this is the opposite, the adjacent, which is 1. So it's going to be square root of 3 over 1. If you check, these values are the same values that you're going to obtain from your calculator. So I want you to find these ones from the 30 degrees, then prove with your calculator. What I'm trying to say is that if you check on your calculator here, we are going to have the same values as the ones that we are having. Just take for an example, let us have this. If we are to consider, sorry for that, I did not want to even show this part. All right, anyways, the tan of 60 degrees in this case like this, which is going to be the square root of 3. All right, we have sine 60, the sine of 60 degrees, which is going to be square root of 3 over 2. So it's one and the same. So I want you to prove using your calculator, find those ones and exactly then prove with your calculator if they are exactly giving us the same thing. So these are the typical questions. I mean, these are the typical formulas and identities and ratios that we need to understand so that we'll be able to attempt typical exam papers. So please revise this part so that we are going to meet again talking about the application of everything, the application of all this part that we have been talking about, especially application of the quadrants. And so for this part, you're supposed to know your quadrants, relationship of your angles from the quadrants. How do you take your angles from a quadrant concept? So knowing this can actually help us a lot. So that's it, guys, for Meson African motives. Till we meet again.